Good afternoon, everyone. Um, Hi. Welcome to the second part of week 3, where we're going to finish off some of our lecture on trees, essentially. And then we're going to go straight into balanced trees. Now, this is kind of the tail end of our last lecture. So last lecture we talked for 2 hours, and this one we'll kind of continue it off, mainly just to talk about deletion quickly. So just to recap for everyone, why am I looking so misty? It's probably because my phone camera, I use my phone for recording, so that might be better. Yeah, my phone just gets dusty and dirty and everything because I take it everywhere. So it's my phone. I wish I could show you, but it's like I need my phone to show you. So phones are great, by the way. I was gonna buy a webcam because I care about you guys having a high quality experience, even though I don't really like being on camera visibly. But yeah, phone cameras are amazing. So yeah, if you ever want a really high quality camera, just use your phone because your phone's probably a good camera. So where we left the last time was we talked about everything. We talked about tree structures, the code for it, inserting into a tree, printing a tree, and then right at the end we talked about these helpful macros, which you're going to start to see more in code. And these macros are essentially the way these work are that when the compiler takes your code, I'll show you this really quick because it's kind of interesting, is that they try and replace this with this. That's what all the hash define does as well, right? When you say hash define true as 1, it just replaces that. And in this case, what it does is whatever's in brackets here, the compiler's smart enough to kind of translate that across. So anytime you see data node, like this, for instance, if you ever see data root, what happens is the compiler converts this to root data. Like that's what it does. And you can actually see this in action. Do you remember when we talked about in the compiling lecture how there was like these 3 steps? There was like the pre-compiling, the compiling, and then like the linking. We can actually do this here if I try and just do like the pre-compiling, it's just something I call it, of bstree.c. Let's try this. So I think it's E. Is it E? Yeah, so the E is essentially like the pre-compile stage. Where it will do some things before it actually compiles, and this is what it outputs. So it takes your C program and it outputs like a similar kind of C program. So it's not compiled yet, because remember the point of compiling is to take source code and convert it to machine code, whereas what's happening here is we're just converting source code to other source code. Now what's really interesting about this, I probably just went straight past it, is I did this line. I didn't add the line, but let me try it here. If instead of saying, root data equals that, I'm going to say data root equals IT. So I'll do something like that in my code. And during the pre-compile stage, which happens automatically when you compile, if I come up to my tree create function here, you'll be able to see that it actually replaced this here. So one thing that happens during the pre-compilation is that it takes all the hash defines and it dumps them in. So there's actually been a change there. And I could show you this as well, for instance. If you just wanted data root to be equal to some constant, like this, and then you just hash define the constant up here to be 5, then during the pre-compile stage, the same thing will happen here. It'll actually take that hash define and put it straight here. So it's a literal copy and paste. And people have been asking, how does it know to do the root translation thing? And it's due to the brackets. So as part of C, hash defines or macros in this case, it sees the thing in the brackets, and it's like, oh, that thing in the brackets is basically a variable, is how it deals with it. Now, at the end of the last lecture, and this is why I'm touching on this, I had some students say, isn't that bad because the style guide says that there's no macros should be allowed? And the short answer is that macros are generally not a great style. You should largely use functions, though there are some circumstances where, like all rules, it's okay to break them, and generally it's whenever we say it's okay, which in this case here is just using these like data left and right hash defines. Because otherwise your code gets kind of crazy and it becomes hard to read because things are kind of like, all over the place. Fun fact for you, I'll give you a really fun fact now that we've learned this. So as you know, these hash defines replace any kind of text you see with something else. So if I hash define, for instance, tree to be my tree, then it will literally replace all the trees in the programs with my tree. So you see anytime I've got tree here, it's replaced it with my tree. One thing we used to do, well, me and a friend used to do this to someone else in RoboCup, which was in C++, which is basically C, is we'd have these hash defines in the code base like this, true and false. And what we would do, we used to do this to mess with each other sometimes, is that at first we started replacing the trues with 0 and the ones with falses while people would go to the toilet. So we'd get on their laptop and we would change those two numbers around, which would just break everything and they couldn't figure out why it wasn't working. But then someone had an even more genius idea to actually replace true with like and I don't remember how to do it in C, but they would replace it with like randint or like a random number generator. And this was the worst thing I might have ever done to someone in a programming context, because essentially what it meant is that sometimes their program true would be 1 and sometimes it would be 0. So every time they ran it, it essentially gave a different output. Anyway, don't be like me. Don't be like bad people. You're all better than that. Waleed says, so even if Style Guide says no can we use them because big man Hayden has blessed us with the forbidden power. I mean, I guess so. It's like there are times in code where you can omit the braces to keep things even more clean. Like, you could do this. And generally I don't like doing that, though sometimes there are times where it's actually more common to do it that way. But yes, short answer is that if we say something's okay, then it's generally okay. So that was the end of macros. Now, we covered most of this lecture. I actually rearranged these slides since our last lecture so that they read better. And we kind of talked about traversal, and we talked about pre-order and in-order and post-order, and we talked about how they're all the same kind of recursive algorithm. It just depends where you print the node, right? And we talked about pre-orders whenever you want to get the value at the value of the node as quickly as possible. So pre-order's typically done for things like searching, where as soon as you hit the node, you want to process the value. In-order's typically done for trying to print things out in an ordered fashion. And then post-order, I think someone pointed out, is mainly used to free things, which is super useful. We talked about these algorithms here because there are 3 different types, and all that really differs in them is when you print it, but otherwise it's the same. And then in terms of time complexity of this, traversal makes a lot of sense because with trees, the best case is 01, because for an infinitely large tree, the best case is that what you're searching for, is at the root. And then the worst case, when you're searching, so just to be clear, this is for searching, the worst case is OH, where H is the height of the tree. Because if you're trying to look for something, then you have to traverse, at worst, the longest branch in the tree, which is the height of it. So for search, and remember, search is where you're going through a tree to look for a value. It's O1 and OH. But for BST, for printing or other things, right? It's not just printing, it's also freeing. Essentially, when you want to traverse a tree to explore everything in the tree, then it's ON, where n's the number of items, because you have to go, you're trying to go through everything. If I'm trying to free all the nodes or print all the nodes, I have to go through everything. So it's ON, because for n nodes, I have to do n steps, essentially. So that's kind of it on traversal. Now, the last 2 things we're going to be talking about today are joining trees and deleting from trees. And then we can move on to balancing trees. So the reason we're actually talking about joining binary search trees is because this is a helpful way to, when you want to delete things. And I might not talk too much about the code. Again, I tend to actually do a lot more coding in lectures, I think, than other people. So my tendency will want to be to do everything, but sometimes that makes us run over time. But essentially, when we want to join 2 trees, it's a lot like linked lists, where, do you remember how sometimes you might get asked that linked list question where it's it might have been on a prac exam or something. I have one linked list and a second linked list, and I want to join them together. And essentially you take, what'll happen is you'll have a linked list here, like this, and then you'll have a linked list here, like this, and you want to join them together, and the function that joins them together takes a pointer to the start of one list, a pointer to the start of the second list. It joins them together, which would effectively, do this. And then the return result is a pointer to the start of the combined list. typically. Or in some cases, it might actually create a whole new list, but in general here, we're assuming that we're not creating more memory. Like, we're not taking two trees and creating a whole new tree that's both of them joined. We're actually trying to join two trees as they are. Sometimes we call that in place, where we're not using any memory. We're not mallocing anything. We're just taking what we have and joining them. So that's what we're doing with trees. We're taking two trees and joining them together. The process, essentially, I just described is we take two binary search trees, we join them into a single one that contains all the items in the correct order, which is the hard part, because like joining a tree, like, like binary tree, like if you had some tree, obviously, like you could join them together. If you had a tree like this, right, you could easily just take that tree and then then make another. You get your second tree here, and you could join them together just by like connecting this one to here, right? That would be valid, but that would be a valid tree, but it wouldn't be a valid binary search tree, right? Because binary search trees are ordered, and this wouldn't be ordered. So we can't just slap it on together. We actually have to think about how you merge those two things together. And that's kind of where the challenge arises from. Now, we talk a lot about ordered trees and balanced trees, if you remember from the start of this lecture. Where was it? So I'm just trying to find the slide. So we talked about ordered trees and balanced trees. So remember that to be a binary search tree, they have to be ordered, but binary search trees can be balanced, which look really pretty, or non-balanced, which looks really ugly. All of these operations like join don't guarantee a balanced tree. So all of these insert, delete, join operations need to maintain order, but they don't always guarantee balance. So when you join two balanced trees, you might get an unbalanced tree. You might get a real ugly tree at the end of that. So the method we use for join is pretty simple. You find the minimum node in the right subtree. So I wonder if I got an example here. I do. So you find the minimum node in the right subtree. You replace the minimum node by its right subtree. And then you elevate the minimum node to be the new root of both trees. Now, text I don't think helps too much if you aren't familiar with the process generally. So let's look at it here. Now, visually up the top, we've got this like thing where we've got two trees represented as triangles, which is personally not my favorite way of thinking about trees. But you can see what it's kind of showing here is that we're taking this like bottom left item here and we're moving it up to the root, and then we're joining two things together. And then if we look at this example here, we have a T1 on the left and a T2 on the right, and you can see that we're grabbing something kind of down the left and we're bringing it right up to the middle and then slapping them all in between. So if we go back to this process, it says find the minimum node in the right subtree. So the right subtree is T2 because we're essentially trying to combine two subtrees into one tree. And remember, whenever I say subtree, we're just talking about a tree because a subtree is a tree as well. So we take T2, the right subtree, and we find the minimum node in it. And the minimum node is always the one furthest to the left. You essentially take every left branch and no right branches. So here I go left, and that's the last left I can take. So that has to be the minimum, right? Because the minimum is all the lefts. It says take that, replace the minimum node by its right subtree, if not empty. So what we're saying here is that we want to take the minimum node 24 and replace it by its right subtree. So essentially we just elevate this 29 here up. So this 29 replaces this 24. But more specifically, right, we replace the entire subtree there. So what I mean by that is that if, say, we have something like this, which I'm also just going to dump in because, I love paint. If we have something like this, it's not always just like 29. Sometimes it might also be like, 25 here, and then like 30. Oh, that doesn't really work. But, 29.5. There's nothing I can put there. But you get the point. Some other number, I'll just call it X. What we're saying is you don't replace 24 with 29. You actually get rid of 24, and you take the entire sub branch up here and you move it up like that. Right, so you're actually taking the whole tree and moving it up. You're not just taking a node. Sorry, I clicked back too many times. Silly. So that's step 2, is you replace 24 with its right subtree. And then you elevate the minimum node, the one we found in step 1, to be the new root of both trees. So you take that 24, you put it right up the top, and then you just join the two trees together as children. Hamish says, what if the minimum node of T2 is less than the root node of T1? Okay, so essentially being asked here, what if the minimum node of T2 is like 9? What was it? So Trent says, what if 24 is a 9? Then it can't be the root, can it? So that's kind of correct. I'm pretty sure. Let me just paste this again. So the question here is, okay, this all makes sense, Hayden, sure, but what happens if this was like 9 here? Like that. What would we do in that case? Well, this one is kind of tricky, right? Because if we take this 9 and then we do what we wanted to and we elevate it up the top here like that, and then we bring the 29 up, and then we join everything, the problem is now we kind of have this scenario where you have numbers on the left of this 9 that are bigger than it, right? But I think, yeah, so Autumnal's kind of getting the point here. So I think the important thing to note here is that getting a fair few questions. So you're all thinking about, you're too smart, is the short answer. So you're thinking about cases that make sense. The main two that people are saying is what happens if there's like a 9 there that's going to break something. The second thing people are saying is what happens if there's duplicates? Like, what do you do with the duplicates? These are all great questions, but what I want you to do is suspend your confusion for a moment, because the reason we're talking about joining two binary search trees is because it's actually the operation that we use when deleting from binary search trees. So it's very rare that you would be using this to actually join two totally disparate trees. It's actually used to recombine a broken tree, which will make more sense. So there are certain scenarios that you apply this in. Yes, there are, as Srika says, Srika, I'm not sure, sorry. Are there any conditions that allow you to merge? There are some kind of conditions, but let's suspend that for a second, because it'll make sense how this ties into delete. We only teach this in this lecture so you know how to delete, right? And here's the pseudocode of it. I'm not going to code this up because we have a lot to chat about, and again, like, we can't code up everything. But I'm not sure if it's in the lecture. If it's not, I'll have to put it there. Do we have a join here? Yeah, so all of this code is floating around the lecture slides. So even though we're not going to code it today, I mean, maybe we can copy and paste it, but it's all sitting there. But yeah, this is the pseudocode. So essentially, it's kind of similar to a normal join, where whenever you're joining two kind of pointers to things, the first step is typically you check if the left is empty, you check if the right is empty, and if either of those two are true, you do an early return, because joining two things where they're not two actual things is easy, because you just return whichever one's not empty. This step here is the traversing step. So this is essentially saying, let's keep going down left. Let's go all the way down the left of the tree until we find a current. So that's the step 1. That's finding the minimum node. This right here is the kind of part of the reassigning stage. So this is us trying to kind of rejiggle and move that step 2, move that node up here, like move 29 up. And then currents left child equals tree 1. So what's really happening here is this step in the middle kind of does it brings the 29 up and it connects 24 to 30. So it basically builds this link here. And then the very last step you'll see here, currents left child equals tree 1, is where you build the left link. So it actually makes a lot of sense, like, because if you understand these things intuitively, like if you kind of read the description of how it works, and then you like look at an example like this, and then you're like, okay, I get the process now. When you look at the pseudocode, you're like, oh, this makes even more sense now. And therefore, when you go to program it, it's actually like really trivial. Because you could imagine if I just said to you, I want you to join two trees based on this general rule, and I just said go code it and see, it'd be a nightmare. Like, I'm sure some of you could do it. I couldn't. I'd be sitting there scratching my head with pen and paper trying to figure out what's happening. Is it just me, or does this seem a bit complicated? I'm not really sure what you mean by that. I mean, it's complicated in the sense that, like, dealing with these tree pointer structures in C is not exactly easy. though I think as an act of joining two different trees, it's not that bad an algorithm, I think. And then the time complexity for binary search tree joining is typically OM, where M is the height of the right subtree, right? And the reason for this makes sense, because if you look at the algorithm, and what do we know about time complexity, which we talked about last week? Generally, it's the loop that kills things, right, with time complexity. In terms of like what's actually taking the time here when you're joining two subtrees is going all the way down the left-hand side of the right subtree. Right, it's like just going down, 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 down. So if you have a tree that has like a height of like 100, then most of the time that's going to happen is actually trying to go down that right subtree to find the minimum node. And in that sense, that's the only part that takes up the time, and the rest of this is all constant time, O1, because you're just rearranging pointers. So pointer rearrangement, it doesn't matter how big the tree is, these steps here always take the same amount of time. That's what O1 is essentially. Yeah, so Chewy, I mentioned that it'll make more sense in a sec when we talk about delete. So we're talking about join to understand how to delete, and you'll understand why it's you'll understand the conditions in which we join. So that's why it's OM. M's the height of the right subtree. So I could write OH here, right? Because we've used that before. We used that for traversal, right? Where do we use that for traversal? We said this at the end here. It's OH for the height. We're using OM here, which also means height. It's just that M is the height of the right subtree. Because in this case, we have two trees. So we need a way to distinguish them, which is N and M. So M is the height of the right subtree. Now we're getting on to delete, which is the last part of this and kind of the maybe the hardest in a way. It's probably just the most like stuff to think about. If you want to delete a node from a binary tree, that's an interesting concept, right? Like if you have this tree here and I said, yeah, can you just delete 30? It's kind of like, like how would you do that right now? Like a linked list makes sense because a linked list is just a line of things. So, you cut one out, you bring it all, join it back together. That's pretty straightforward. But how do you join a tree when you delete a parent that has two children? That's kind of trickier. So when we're dealing with a tree, there are, and we want to delete a node, deleting the node should be easy. You find it, you free it. But the question is, how do you join the tree back together? How do you link everything up so that the tree still works after you've deleted something? And there are essentially 4 cases to consider when it comes to deleting from a tree, right? And the first 3 are actually really simple. So most of the difficulty in binary search tree deletion all comes from the case where you're deleting a node that has 2 subtrees. That's everything else is pretty easy. Jeremy says, do the children's become orphans? So the plan is that we don't want the children's to become orphans because if they become orphans, then the tree doesn't work anymore. So that's what we're trying to prevent here. So let's look at these 3 cases. The first one is, what happens if we try and delete from an empty tree? So that should be easy enough because what is an empty tree? An empty tree is when you have like a variable t that points to null. Well, if someone tries to delete a node from an empty tree, you get an empty tree. So there's literally no work to do there. It's just an early if, and then you return early. Then we have 0 subtrees. Okay, so what happens if... Let me just maybe go back to the previous thing we had. What happens if someone says, I want to delete 32 from a tree? Right, so think about it intuitively. Don't worry about algorithms or anything. And the answer is that you just delete 32 and you make sure that its parent points to null. That's the only hard part of that, right? Like deleting is just freeing the node. You take the node, you free it, just like a linked list. And then you have to make sure that the previous one points to null. So it's very linked list-esque there. Also not too hard. I've got more detailed slides on these here, which we can go through, but I'm just running through them once. What happens if a node has 1 child? Now we don't have this example here, but I'm sure I could find one on another. I'm just going to go down because it's all in the slides. Case 1, empty tree, we talked about that. Case 2, 0 subtrees, we just talked about that. You just delete it. Really simple. Case 3 is 1 subtree. This one is also a little bit simpler than case 4, but these kind of get progressively harder. So if I said to you, I want you to delete P, right? It only has 1 child. Now what's really handy about this is that, again, it's like a linked list in the sense that you simply have a parent before it and you have one child after it, which becomes a next. So your job is to pull out the node, delete it, and join those two sides up. So it's kind of like case 2, except instead of getting G to point to null now, you're actually getting T, the equivalent, to point to R, because you need to have T kind of skip over P, the one you're deleting, and then point to R. Diora says, Diora says, what if R is greater than T? It's not, because it's a binary search tree. So before you've tried to delete from it, R would be less than T by virtue of where it's placed in the tree. Because everything to the left is always smaller, everything to the right is always bigger. Okay, and then for case 4, and this is the hard one, and honestly, like if you're talking about deleting, I think this is where 80% of the pain comes from, right? It's this case 4, which is when you need to delete a node, right, with 2 children. Now there are 2 methods to the delete, and I don't know if we'll talk about the second one, but the first one is to use a join, which is actually really interesting, and I hope this kind of answers your questions previously. And maybe I'll swap these slides around next time, because you're all too smart. You're all like, well, this join's not going to work under all circumstances, and I'm like, yes, yeah, true. So in this case here, if you have a binary search tree with M that has 2 children, and this could be true for any node in the tree, it doesn't need to be the root. What you do is you remove the node M, and then you join the 2 subtrees. Because if you imagine for a second that what we actually have here is that when we get this tree, it's so small, such a cute little tree, is we say, okay, we're going to delete M. So what we do is we free M after we've gotten the pointers, and what we're left with is 2 subtrees. That's actually what we're left with. So we're left with T1 over here. Oh, that's so tiny. And we're left with T2 over here. And what you notice about these 2 subtrees is that everything in the left subtree is smaller than everything in the right subtree. That makes sense, because the original tree, before it was broken into 2 orphans, because everything to the left was smaller and everything to the right is bigger. So back to those questions people were asking about, what happens if the 9 is there? And the answer is it won't ever be, because the trees that we're using this join algorithm on, everything in tree 1 is bigger than tree 2. Okay, and that's a great point. I love that you've all raised that. That's probably something I'd add to the lecture slides, just to like make it clear, as be like, oh yeah, this only works when T1 is smaller than T2. So thanks for being so prudent on that, everyone. So yeah, that's how you join it. And then what's great is you just take these 2 pointers and you just follow the algorithm we did in the previous slide. That's it. You just take it and you follow the algorithm. And then what would that do? This would take the P here. Like we know you go all the way down the left, it would take the P, it would move it to the top, we would move this subtree up, and then it would rejoin everything here. And that would be your new tree, right? And similarly, the complexity of this is going to be OM, where M is the height of the right subtree. Cool. The successor method. So I think the join method's kind of nice. I don't know why I like it. I couldn't give you a good reason. But there's another method which I don't use as much, which is where you try and delete M. It says for the node, its right child becomes the new root. Then attach, so the right child T becomes the new root, sure. Then attach the node's left subtree to the minimum element of the right subtree. I think this one just like gets a little bit confusing in a way. So, you know, just to flow through it again, it's like the right child becomes the new root. So let's just, again, grab a copy of this, and we can step through this one slowly. So it says that if we delete M, let's delete M, that its right child becomes the new root. Okay. So its right child kind of comes up here and is now at the top of the tree. Then attach the node's left subtree to the minimum element of its right subtree. So the node's left subtree, when they say node, they're referring to the root, which is this. So this is the left subtree of the original root, right? It says take this and attach it to the minimum element of the right subtree. And what do we know? The minimum element of a tree is when you start from the root and you go all the way down the left. So this ends up getting glued on here like that. And that's my bit of an ugly tree, but that's kind of what it looks like. And again, just to recap, it's like we get rid of the root, which goes, and then we take the left subtree, attach it to the minimum element of the right subtree, and then the t gets escalated to the top, like that. So that's your new tree, where t is the new pointer to the top. That one's also fine. It's not really like that much harder or different or anything, just two different methods. I don't think there's a benefit of complexity with these, because if you think about it algorithmically, this successor method as well, deleting the root node's constant time, grabbing the left subtree's root node's constant time, the only non-constant time operation is to traverse the right-hand tree to find the minimum node, because you might have to go down the whole height of the tree. So this one is OM as well, where M is the height of the right subtree. And what do we got? Yep, so we have some pseudocode here. What does this one look like? While current's left child is not empty, parent's not null. Yeah, so that one seems easy. Yeah, you can do what you want. I mean, I'm not going to fight with you on it. I'm not saying I'm a genius. Like, I like a lot of things. I like Sublime text instead of VS Code. I don't think that's particularly rational, but it's true. But no, there's no difference in complexity, and this algorithm here, I think, looks like it's for the successor one. They're both really similar though, because they both kind of involve you delete a root. It's just whichever one. Is it the same code as join? I was like looking at it and I'm like, yeah, I was like, this looks super similar. Interesting. All right, let me dig that one up. That looks like a strange little error. I think. Yeah, it is join. It takes in two arguments. That doesn't make any sense. Derp. So if you can't see my brain being like, which one is this? I'm just having a look for it because I stole it from. Yep, I'll update that after the lecture. But in the meantime, if you really desperately want to see it, this is kind of what it looks like. Because I was like, I'm pretty sure the method that I wrote up used the join. We use the join. The one thing I kind of like about the join method, and maybe this is just like a thing, is I like anything that breaks up a problem into subcomponents. So I really like how the join algorithm, it's essentially like it does the traversing, breaks it, and then it delegates it to something else. So anytime in my life I can break a problem up into two things is even better. So I'm like, oh, deleting's easy. We'll delete the node, get two new subtrees, and then we'll pass it off to Pablo over here to do the rest. So that's probably why I like it. I'll update the slides with that. Sorry, that's probably just that's just mistakes. But yeah, so deleting is pretty straightforward. Time complexity is the same. Now this one, you'll see that we say that the complexity is OH instead, and I think I said OM before. And the reason it's OH here is because when you're actually doing the deletion, there's no sense of left and right subtree, right? Because you haven't actually split them yet or done anything. So typically BST deletion's OH. And most things in binary search trees are like just OH, right? Like insertion, deletion, like they're all just kind of OH. Nothing is, you've kind of got these three camps. You've got constant time operations, which don't really exist that much because you can't do much without traversing. You have OH, which is pretty much most things. And you have ON in the cases where you need to traverse everything, like printing and freeing and stuff like that. If you want to learn more about these binary search trees, we'll loop back to this if we find some spare time, but for now I want to keep moving on. There is the code here. This includes some of the stuff we're about to go through next, but this is the code to delete, there's the code to join. We did the printing yesterday. This is code to free. What you notice about this one here is that here we're actually doing a traversal. It's just post order, because you'll see that this is the exact same here as if I go back to traversal. It's just post order, which is explore left, explore right, and then do something at the node. So this one here is like explore the left one, explore the right one, then do something at the node. Are you able to use parts of this code in accessible work? Absolutely, you can use all of this code. I've been slowly modifying this code as I find problems with it, because so I didn't originally write most of this, but I've been trying to clean it up because I don't like some of the inconsistencies that I've seen in it. And that includes mainly just little, like you'll notice here that in the slides I have, where did I put it? In the slides, I've started to try and use a bit more of a standard ADT format, like tree create, tree destroy, tree insert, and tree print. You'll notice that some of the code here just has different names. So this is just me. I've been trying to migrate some things across because I think that I generally find, in my opinion, I think that, this is just my opinion, is like naming conventions work better when it's noun than verb, because, you know, it's kind of clearer, like, because then all the different verbs you can do on a noun are kind of organized visually, because it's like tree this, tree that, tree this, tree that. So I've just been kind of going through. So if anyone is like desperate to use these urgently, then you might have to change a couple of those. But, you know, this is just something I do late at night. Let's just go and update them. So yeah, and then lastly, someone said, what's the point of trees? Like, what's the practical use case for them? That's a really great question. We actually in a C++ lecture the other night, we discovered that in C++ you actually have this type called a set. And C++ is just another programming language, and I'm just trying to see if there's some examples of its usage so that you can kind of get it. Maybe not. But in C++, you have a set type, and this is kind of true in a lot of languages, because sets, which we've seen from previous lectures, sets can either be ordered or unordered, and that is that, like, some sets of numbers, and sets are just collections of numbers with no duplicates, or collections of anything. Some of them have no sense of order, right? Like, we're kind of familiar with this from if you've done a Python course and you know dictionaries, you know there's a data type that isn't ordered. There's no way you can say get me that in order, because it doesn't have an order. And then there are other data types which do use order, where it actually matters. So for an ordered set, that's actually one of the most common use cases of trees, because think about what a tree is. It's like, it's literally an ordered set of numbers. Like, a set is just no duplicates, and it's ordered. So if you store a set of numbers or a set of anything as a tree, you have, you know, OH insert, OH deletion, OH search. Like, it's a really quick operation. So you can have 1 million items in a tree, but, you know, the lookup time is like nearly instant for 1 million items because of the logarithmic nature of the time complexity. So super, super useful. If you need, like, I would say trees are pretty much used in any context where you would need, you need it to be sorted, and you didn't need random access. Random access is in looking up an element, like, instantly, like an array would or a hash would. But generally speaking, most data types you kind of see are either going to be fundamentally, like, they're probably either going to be arrays, they're either going to be trees, like basically linked lists on steroids or something, or they're going to be hashes or some kind of hash table or hash map. There's like other kind of things there, but for me at least, they're kind of the three big data structures. And we talk about graphs and stuff in this course, but graphs and trees are all kind of really the same. Autumnal says sorted, quick, but not random access and easy to modify. Yeah, lots of different things. But trees are used to organize and collect lots of things. Anytime you have a parent-child relationship where parents can have multiple children, it's also used there. Not for performance reasons, but because of just good data structure reasons. Like, some things just make sense to be stored as a tree, like a folder system on a computer. Even if you don't need it to be like ON, OH, or anything like that, it's just kind of quicker. Anyway, it's just kind of more organized. So sometimes it's like the algorithms motivating you, which is like how fast it is to do stuff, and other times it might just be the data structure. Makes a lot of sense to store it like that. Anyway, that's it on the introduction to binary search trees, which I'm just going to wrap up this recording. So thank you, everyone.